Okay, a fairly quick one on electromagnetism, the ways in which electric currents, moving charges, create magnetic fields, and then the ways in which those magnetic fields affect the moving charges. So we've got a situation, two horizontal wires, parallel, 0.37 meters apart, each carrying a current of 1.7 amps in the same northerly direction over a distance of 21 meters. All right, so let's draw that for a second. So we've got our two wires. Oh man, not so easy to draw with a stylus. They're supposed to be straight and straight in that direction. They are 21 meters long. .37 meters apart, and they're each carrying a current in the northerly direction of 1.7 amperes. So this also, if I've got room, 1.7. Okay, so that's our situation that we've got. So if we go back to the question, find the strength and direction of the magnetic field at the location of the eastern wire due to the current in the western wire. And I've given a hint here, the right-hand grasp rule. So to find the shape of the magnetic field around a current-carrying conductor, we grasp it with our right hand in the direction of current flow. So in this case, the current flow is northerly or up the page. So if we grab that western or the left-hand wire with our right hand, with our thumb pointing upward, then our fingers curl around the wire and show the direction of the field at every point around the wire. So at the location of the eastern wire, the right-hand wire, those field lines are going downward into the page. So the direction of the field is downward, or downward, because we've said they're parallel, so they're horizontal, parallel to the ground, and going north-south. So it's going downward toward the ground is the direction of the field. The strength of the field, we have an equation which is B equals mu naught I over 2 pi r. So mu naught, 1.26 by 10 to the minus 6, the permeability of free space, times I, the current, is 1.7, because we're just looking at the current, the magnetic field due to the western wire alone, not due to both of them, over 2 times pi times the radius, which in this case, the distance between them is 0.37 meters. Ends up giving us a field of 1.06 by 10 to the minus 6 Tesla in a downward direction. Okay, so that's the first one. We've got both the magnitude and the direction of our new field. Let's move it up a little bit. Question 2. Find the magnitude and direction of the force acting on the current in the eastern wire due to the western wire. Okay, so we know that we've got a current flowing north. We've got a field going downward into the page. What's the direction of the force going to be on it? If we use the right-hand palm rule, so flat palm, hand out at thumb out at right angles to the fingers. Fingers are the directions of the field lines. Thumb is the direction of the current flow. Palm is the direction of the force, the push. So the eastern wire, the right-hand wire, is going to be pushed left towards the left-hand wire. It's going to be attracted to the other wire, or experience a force toward the other wire at least. So now we know the magnitude of that one. The direction, is going to be west. It's going to experience a force to the west. And to find the magnitude, we've got 2B equals, sorry, I'll try that again, F equals, because we're trying to find a force. F equals BIL sine theta. Now that theta would be if there was an angle between the force and the field and the direction of the current, but in this case there's not. The angle is 90 degrees, sorry, between those two things, and so sine of 90 is just 1. So we don't have to include that in the calculation because it just becomes times 1. So equals B, we just worked out the magnitude of the field before, 1.6 by 10 to the minus 6, 1.06, sorry, by 10 to the minus 6, times I, the current in the new wire that we're looking at, 1.7 amps, times the length, 21 meters. And as I said, sine theta just ends up being 1 because there's this right angle between the two, between the field and the direction of the current. And that gives us overall 3.8 by 10 to the minus 5 newtons. And the direction, as we'd established already, is westward. And then the third question isn't a calculation. Excuse me, that cold's still hanging around. The first question isn't a calculation. It's just a think about it question, I guess. So what we're asked is, what's the direction of the force acting on the western wire due to the current in the eastern wire? Now there's a number of different ways we can approach this. One is to say Newton's third law. So there will be an equal and opposite force, a force of equal magnitude in the opposite direction acting on a different object. So that would suggest that the force on the western wire is to be toward the east. They're both attracting each other, in other words. They're being pulled together and of the same magnitude. Another way is to actually do the calculation, the same calculation we just did. If you quickly do the right-hand rule on the eastern wire, the right-hand wire, you discover that the field is coming up out of the page at that point. And if you then do the right-hand palm rule, you discover that the force is indeed towards the other wire, to the east. So I'm not going to write a huge amount here because I've talked to it, but the force is to the east. And we could establish that by Newton's third, or just by going through the steps that we just did above and figure it out that way. Or we just actually could remember that when there are parallel current carrying wires, if the currents flowing in the same direction, they're attracted. If the currents are flowing in opposite directions, they repel one another. Lots of possibilities.